Hello everyone, welcome to my class. In today's class, I'm going to cover applications of integrations to physics and engineering. So let me start the class right away. First, some terminologies. Mass equals to density times area. We denote density by rho, area by A, mass by m. So we have formula m equals to rho times A. Moments equals to mass times distance from the axis. So there are two moments. So suppose mass is situated here with the coordinate x and y, then moments of the systems about x-axis equals to m times y, because y is the distance from x-axis to that mass, and we denote by mx. Similarly, moments of the system about y-axis is denoted by my and is defined as mass times the distance from y-axis, which is x, so m times x. Center of mass, we also write CoM, in two-dimensional is a unique point x bar y bar of a thin flat plate at which it balances horizontally. The entire mass of the plate is concentrated there and is defined by x bar equals to my over m and y bar equals to mx over x. So in the diagram here, I give you the rectangular thin flat plate, and if I put a fulcrum here, it's balanced. That means that point is the center of mass. Great. So for example, I can balance my iPhone here. So that means I'm finding this point which is denoted by x bar y bar, and we call that point as a center of mass. Great. Let's move on. So for a lamina with uniform density rho occupying the plane region R under the curve of y equals to fx, between two lines x equals to a and x equals to b above the x-axis, we have the following. So let's see here. So in this diagram, our flat plate occupies this region R, which lies below the graph of y equals to fx above the x-axis, and between the lines x equals to a and x equals to b. Then we compute the following using integrals. First, the total mass is rho times A is the area of the regions, which is given by the definite integrals of fx from a to b. The moments my equals to m times x, which is rho times definite integrals a to b x times fx. Similarly, mx equals to m times y. So rho times, here is the y distance of this flat plate using symmetricity. This distance is simply y over 2. The total length is y. Up to here is y over 2, which is fx over 2. So replace y by fx over 2, fx dx. Let me scroll down. Great. And then fx is square, 1/2 outside. So then mx equals to rho over 2 definite integrals a to b of fx, outside is square, dx. Now center of mass, x bar equals to my over m. We know my is here, so definite integral a to b x times fx dx over m is here, rho times a to b fx dx, and we cancel the rho here. Similarly, we have the formula for y bar, which is mx over m. It turns out that y bar equals to 1/2 definite integrals a to b fx, outside is square, dx over a to b integrations fx dx. Great. So in general, if the region R on the plane lies between two curves, y equals to fx and y equals to gx, where fx is greater than or equals to gx on the interval ab, then our respective formulas above becomes here. So total mass, So keep in mind that we have to take care of the difference of the functions here. So total moments and center of mass. So I think it is given here. So it may be better me not to read this one. Awesome. Great. Now one final remark. The cancellation of rows implies that the location of the center of mass is independent of the density. So without loss of generality, we may take the density rho equals to 1 in our computations. Awesome. Now let's move on. Let's do example. Example 1, the point masses system. Find the moments and center of mass of the system of objects that have masses m1 equals to 3, m2 equals to 5, m3 equals to 2 located at the points m1 located at point P, m2 is located at point Q, m3 is located at point R respectively. Solutions. So let's find the total mass. Oh, that's better. So the total mass m equals to 3 plus 5 plus 2, which is 10. And let's compute the moments. The moments mx equals to 3 times the distance from y-axis. This is 1 of this point P. Similarly, 5 times negative 2. Similarly, 2 times 2 and add them all, which turns out to be 2. Similarly, my equals to first mass times the distance from x-axis, which is negative 1, so 3 times negative 1, plus second mass times the distance from x-axis of the point Q, which is 2, so 5 times 2. Similarly, third mass times the distance from x-axis of point R is 3, so 2 times 3, add them, 13. Hence, center of mass is by formula x bar y bar equals to my over m comma mx over m. It turns out that 13 over 10 comma 2 over 10. By simplifying, it turns out to be 1 over 5. Great. I hope this computation makes sense to you all. Now let's move on. Example 2. Find the coordinate of the centroid of the region in the plane bounded by the curves y equals to 2x, y equals to 0 and x equals to 1. Sketch the region. So let's begin the solution. So let's look at the diagram first here. So this sketching part. So here y equals to 2x is this diagonal line, y equals to 0 is x-axis, x equals to 1 is this vertical line. So our region is this region, which lies below y equals to 2x, left from x equals to 1, above from y equals to 0, this region. And let's say its center of mass, also called centroid, is this point x bar y bar here. First, let's find the area. Area equals to the different integrals. Here x equals to 0 to 1, and the y means fx dx means 2x dx. So integration of 2x turns out to be x square. Put limit x equals 0 to 1. Simplify, it gives us 1. So our area is 1. So that means mass equals to rho times A. So rho equals to 1. That means mass also 1. Next, moments are my equals to the definite integrals x times 2x dx. Then integrate here. To constant as it is, integration of x squared becomes x cubed over 3. Put value x equals 0 to 1. Simplify, it gives us 2/3. Similarly, mx equals to, from formula, 1/2 function is square, y equals to 2x square, definitely equals 0 to 1 dx. Then take the integration, simplify, it gives us mx equals to 2/3. And center of mass is x bar y bar equals to my over m comma mx over m. We know m equals to 1, so it turns out to be 2/3 comma 2/3. Awesome. Now let's move on. Example 3. Find the centroid of the region on the plane bounded by curves y equals to x square and x equals to y square. Sketch the region. Solutions. First, let's talk about the diagram. First, sketch the graph. Here y equals to x square is this parabola opening upwards, and x equals to y square is this parabola opening to the right. So the intersection point is, let's solve these two equations. Then it turns out that x equals to 0 and 1. So they intersect at x equals to 0 and x equals to 1. So our region is here, which lies between y equals to x square and x equals to y square. So let's find this point whose coordinate is x bar y bar, which is the centroid. Awesome. So first, let's find the area. Area A equals to definite integral 0 to 1. Then the top curve minus the bottom curve. So top curve is here, y equals to radical x, and bottom curve is y equals to x square and then dx. Take the integrations, put the value x equals to 1 and 0 and simplify. It gives us 1/3. Next, let's find the moments. So my equals to definite integral 0 to 1. This is by formula x times the difference of the functions. Next, foil x inside and take the integrations and put the value x equals to 0 and 1. It turns out that my equals to 3/20. I hope this computation makes sense to you all. Let's move on. Similarly, mx equals to, by formula, 1/2 definite integral 0 to 1. Then the difference of the square of the functions. Simplify, take the integrations, put the value x equals to 0 to 1. It gives us 3/20. So the center of mass is x bar y bar equals to, use formula, it turns out to be 9/20, 9/20. Great. So now let's move on. Quick remark. Great. Let me give you the final remark. The volume of the solid obtained by rotating a plane region R about a line is equal to the product of the area of the region and the distance traveled by the centroid, which is the circumference of R during one full rotations. So let me revisit example 3 and verify this remark. So in example 3, we have two curves, y equals to x square and x equals to y square, and we found the centroid of the common region here. So the centroid is x bar y bar equals to 9/20, 9/20. So then let's rotate these regions around the y-axis. Then this generates this solid here. And let's compute the volume using cell method first. So towards my right side here, so I computed the volume using cell method. So volume equals to, so for the cell method, I need to take a slice here, which is a parallel to the axis of rotation. So I'm taking the slice here, the vertical slice. Then by formula, volume equals to definite integrals x equals to 0 to 1 to pi x. X is the radius. So the radius is the distance from axis of rotation, which is y-axis, to that region. So that means which is x. This distance is x. Then the times. Then I need this height here, which is from here to here, is given by y equals to radical x, and from here to the inner curve is given by y equals to x square. So that's why this is the top curve minus the bottom curve here, radical x minus x square dx. Foil x inside and take the integrations and put the value x equals to 0 to 1. It turns out that the volume of the solid generated by revolving these common regions about the y-axis is 3 pi over 10. I hope this computation makes sense to you all. Now let's talk about this volume. This remark says the volume of the solid obtained by rotating a plane regions about a line we found, now is equal to the product of the area of the region. So first find the area of the region and multiply by the circumference of the regions, because the distance traveled by the centroid, the distance is 2 pi r. So here is a centroid or center of mass. Then this is making one full rotations, is this circles here, and then its circumference is 2 pi this radius. This radius is the x value, which is 9/20. So first find the area. So here area of these regions we computed above. Area of these regions bounded by y equals to x square and x equals to y square is 1/3, and circumference of the circle with radius 9/20 is 2 pi r, which is 2 pi 9/20 is 9 pi over 10. Hence the volume equals to this area times this circumference. So 1/3 times 9 pi over 10, it turns out that 3 pi over 10. These two are equal. Great. So we finish these sections. Thank you.